Besides precipitation reactions, which involve two sets of ions coming together to form a solid, we also talked about acid-base neutralizations, typically involving Arrhenius acids and bases, those materials that release H plus in solution, and Arrhenius bases, which typically have a hydroxide ion, though there are other types of acids and bases, like Bronsted acids and bases, which are more behavioral. Still, regardless, these compounds can undergo neutralization. In a neutralization reaction, the hydroxide ions react with the hydrogen ions to create water, and usually some sort of salt that remains aqueous in solution, but not always. The water comes out as a liquid, and these two aqueous solutions, again, the hydrogen ions and the hydroxide ions combine to form H2O. Now, of course, for every one hydrogen ion and one hydroxide ion, you get one water, so you can actually, for polyprotic acids, things like H2SO4 and H3PO4, these have multiple protons, and so forth. They require multiple hydroxides. In this example, 2 hydroxides to 1. So we can use this idea of a neutralization. Technically, a neutralization is when the amount of acid is exactly enough to react with the amount of base. Right? Not necessarily 1-to-1, but they are often related. And we use this in very specific cases, and one of the cases we're going to talk about are titration, and in bulk neutralizations where you mix solutions, which often turn into limiting reagents problems. So let's take a look at a typical acid-base. And this is where we use molarity. So let's take a look at the problem. How many milliliters of a 3.35 molar solution of HCl are required to neutralize 0.5 grams of NaOH? Now, in this case, it's not shown, but we need a balanced chemical reaction. 1 HCl plus 1 sodium hydroxide generates NaCl plus water. If that stoichiometry was 2-to-1, we'd have to take that into account. So we look at the problem, we have a volume of acid, and we have a mass of our base. In this case, grams of NaOH, and a 0.350 molar. In this example, we're looking for a volume of acid given a mass of base and a concentration of acid. So here's our concentration, and here's our grams of sodium hydroxide. So how do we use this? The question is asking us for a volume. How do we relate volume to the quantity? The only relationship you have is volume and moles via molarity. So if we know the molarity, we can relate volumes to moles. So let's take a look at that. Well, we do have a molarity, but this is moles of acid to volume of acid, which is what we're looking for. So nowhere in this problem is moles of acid. So what we have to do is relate the moles of base to the moles of acid, because once we know how much base we need, that tells us how much acid we need. For every 1 mole of sodium hydroxide requires 1 mole of HCl. After that, we have a simple procedure. Grams of sodium hydroxide, which we would convert into moles of sodium hydroxide. Well, that's easy. That's a molecular weight. And then from there, moles of sodium hydroxide, we'd convert that into moles of HCl. Again, that would be our mole-to-mole, our equation, mole-to-mole relationship. And lastly, for moles of HCl, then we would use the molarity to predict the volume. Get things into the mole where possible. So we have 0.5 grams of sodium hydroxide, and from the molecular weight of sodium hydroxide, turns out that the molecular weight of sodium hydroxide is 40 grams. Sodium hydroxide, 1 mole. Sodium hydroxide, for every 1 mole sodium hydroxide, that's equivalent to 1 mole of HCl. And again, this is overkill, Dan. It's a one-to-one relationship, but you don't want to use your units. We want to work on those relationships because sometimes the stoichiometry is not one-to-one. And then here is the hard part. Moles to volume, liters. The mole to liter conversion is from our molarity. Unlike any of the other conversions, this is not a one-to-one or for every 1 liter or for every 1 mole. This is usually not always whole numbers. What this says is 0.350 moles is equivalent to 1 liter of solution. So the number of moles would be 0.350, 1 liter. And out would come an answer in liters. It says it would require 0.0357 liters. The question asked us for milliliters. So a quick conversion, 35.7 milliliters would be produced. Now, let's set up and do another problem, exactly the same, using a different formula. And here we have the fact that 2 HCl are required to react with magnesium hydroxide to produce 2 waters and magnesium chloride. I'll let you set that up. The molecular weight of magnesium hydroxide is equal to, again, the process is very similar. Grams of our base converted into moles of our base, just like we've been doing for the past 3 weeks. Moles of base to moles of acid. And then from there, we can use the molarity to figure out the volume of acid. So if you set up the calculation, it looks pretty much the same as our other one. Gram to mole conversion, a mole to mole conversion. Again, this is the dangerous part. Mole to mole, we have to take into account the fact that there's 2 HCl for every 1 magnesium hydroxide. And then once we're in moles of HCl, we use the molarity to produce liters. And again, in the molarity statement is equivalent to moles in 1 liter, and then we can set that up. And then this last step is just a metric conversion that we tack on the end. As you get more adept at these, you can start to combine these 2 statements. So, very typical how you use molarity. Molarity and a volume give us the number of moles. Molarity and moles give us the volume. In fact, you can sort of think about these in this sort of way. Right? Given any 2 of these, you can use the other one. So for instance, if we want molecular weight, we can take the number of grams and divide it by the number of moles. If you want moles, you take the grams and you divide it by the molecular weight. All right? These, again, all stem from our definitions. Same with atoms or molecules. You have number of moles. If you want the number of moles, you just take the atoms and you divide it by Avogadro's number. Now with molarity, it's a little bit different because of the location of the mole in this sort of setup. You take the mole, if you want moles, the liters times the molarity give us the number of moles. If you want molarity, moles divided by liters. But if you want liters, you can do molarity moles divided by molarity, and you would get your answer, right, in liters. And this is just a quick way, a mnemonic. And these all stem from what our definition of molarity is. Molarity is equal to moles divided by liters. So you draw a little equal sign and you can see these. Same with one of the ones that throw people is we don't often think about it, but if you know the grams of material and the number of moles of material, you can use that to calculate molecular weight. We don't often think about calculating molecular weights, but it's actually one of the easy things to do, given number of moles, which you can find a number of different ways. All right? So, in many ways, molarity is a lot like molecular weight. And you use it in a very similar fashion, and it's to relate the idea of of moles to volume. Right? So that relationship is always through molarity. So look for ways to convert your volumes into moles using a molarity. Those are situations where you're told the molarity. So those are very different problems than if you're asked to find the molarity. Right? So in two very different strategies. We talked about the finding the molarity in the other example, which is moles divided by liters done. All right. Moles of the right thing, though, that's the secret.